Welcome to this final video in our third lecture on hydrogen, and now we'll be looking at some of the trends and also hydrogen bonding, which is intrinsically linked with the trends we see in hydrides across the periodic table. So first off, here is the periodic table of hydrides. So what we've seen before. We've got the S block hydrides here, the P block hydrides here, and we haven't talked about the transition metals in the middle. And we've already got quite a lot of the trends shown in different ways on this one periodic table. So on the left hand side we have the weakest bonds, and on the right hand side we have the strongest bonds. Something we highlighted a lot in the last lecture was how stability decreases down a group, and we see that here, stability, highest stability at the top, lowest at the bottom. And this stability is linked to the bond strength decreasing as we go down each of these groups. If you remember, we called them hydridic hydrides on this side and protic on this side because of the electronegativity difference. So in the P block, especially here, the halogens or the oxygen, say, or sulfur are more electronegative than hydrogen. So they end up having a -1 oxidation state, and hydrogen has a +1, which is protic. And then on this side, hydrogen is the more electronegative, so it has a -1 oxidation state, and it's hydridic. And then as we go across the periodic table also, the acidity increases. So if you remember, when we reacted the S block hydrides with water, with the exception of beryllium, if you remember, that's more stable. So these, when we reacted with water, formed an alkaline solution, whereas when we talked about the hydrogen halides, these were acidic, and as we went down the group, actually become more acidic. Now, the one thing I did say I would explain is the reason for the trend in stability. Like, why are these bond strengths higher at the top than down the bottom? And if you remember, we talked about, I think it was in the first lecture, how bonding is stronger as when the orbitals, atomic orbitals, overlap better. So hydrogen's a very small atom. So we've got hydrogen here. If we make If we make a bond with fluorine, say, or oxygen, it's not that much bigger. This is not to scale, probably a little bit bigger than that. So if you say this is oxygen, the orbitals are fairly similarly sized. They've got good overlap. But then if we try and look, for example, with bromine, this is already further down the periodic table. So instead of being in the 2 shell, we've got the 2 shell here, 3 shell here, it's in the 4th shell. The atomic radius, if you remember, increases down the group because they're in a higher shell. So if you've got bromine being absolutely massive like this, the overlap with the very small hydrogen is going to be very little. So the bonds won't be as strong because the atomic orbitals don't overlap so efficiently, and therefore it gets weaker. So this decrease in stability down the group is related directly to the increasing atomic radius down the group. Now we've got some more trends here in the melting points and boiling points, and I've given the spoiler away in the title. They're related a lot to hydrogen bonding. So if we start by looking down here at group 14, in both the cases, you can see this has got a fairly linear trend. It bucks it a little bit here in the melting point, but as you go down the group, the boiling point increases and the melting point increases. And this is due to the relative molecular mass, and also it's increasing interactions down here. They are London dispersion interactions, or sometimes they're just referred to as London interactions and sometimes just dispersion interactions. And these are interactions that always exist between molecules in the gas phase, liquid phase, and they're explained very well in the book as well. And this is essentially because of polarization. Now, we touched on polarization at the end of the last lecture as well. So if you think about the electrons, if we draw an atom, say, in the gas phase, the electrons are never equally distributed over this entire atom. There's always going to be the electrons at a specific given point in time. If we took a freeze frame, the electrons, say, might be actually on this side of the atom. So you get a delta minus because that's where the electrons are, and this side will have a delta plus. And this will happen with all of the atoms in the gas or the liquid. So when they come across each other, there will be very small plus or minuses, like partial charges, that interact and attract each other. And as the molecules get larger, as the molecular mass goes up and the atomic radius, you remember we said bigger ions in the last lecture are more polarizable. And this exact same thing happens, so that London dispersion interactions are larger with larger molecules. And since these have an attractive characteristic, that's why as we go down the group and have larger molecules, these London dispersion interactions increase, and we end up getting a higher boiling point and a higher melting point. Then if we look at group 15, 16 and 17, we see that the first one, well, for the rest of them, they do follow this nice linear trend. But the first one, HF, ammonia and water, are much higher than we were expecting. So there must be something else occurring that's causing this increased stability in the first three. And the reason for this is hydrogen bonding. So what hydrogen bonding is an attractive interaction between a hydrogen atom. Doesn't just have to be, say, in HF. It does say a molecular fragment, XH, in which X is more electronegative. So these do happen in large organic molecules, say, if you've got an oxygen hydrogen in there, where X is more electronegative than H. So for this example, let's look at water, say. Oxygen is, we've got it already drawn down here. There we go. So oxygen's much more electronegative than hydrogen. So again, we've got these partial charges. We'll have a delta minus on the O because it's more electronegative. It wants those electrons, and then delta pluses on the hydrogens. And then again, these delta plus, delta minus will attract. And these are much stronger than the interatomic interactions, like the London dispersion interactions we were just talking about. Hydrogen bonding is really quite strong. And it's mainly with nitrogen, oxygen or fluorine. It can occur with other elements. So with chlorine it happens quite a bit as well. I mean sulfur, phosphorus, and even to some extent carbon, but it's really nitrogen, oxygen and fluorine that you'll see this hydrogen bonding with. And that's because they're the most electronegative. There's the most difference between the electronegativity of these three and hydrogen. So they form the strongest hydrogen bonds. Finally, it's because of hydrogen bonding that ice ends up being less dense than water. When we've got them in the liquid phase, the water atoms can really just bump around, move around quite well. But as you drop the temperature and they crystallize out into ice, this hydrogen bonding is really quite strong and has an effect on how the water molecules orient themselves in the solid structure, in the crystal lattice, and they form very large structures with big open spaces. So that means the volume required when ice is solid, water is solid as ice, is much larger than when water's in the solution. And there's some nice diagrams in the book showing the sort of structures of ice. So here are some questions that will test everything we've done in this lecture really. So don't do question 1 or question 8, but 2 to 11 should be good. There's some bits in there that we didn't touch on exactly, so, but it tells you in the book which pages to go back to or which sections to read to get an idea. If you have any questions, you can obviously ask them in the discussion session. And also, when I manage to get time, I'll go through each of these questions and make a video explaining how to do each of them and upload that also for your revision.